The practice quiz, just like the quiz, will expect you to use Table G to determine solubility of different substances, Table H for vapor pressure and boiling point, and the equations for concentration and parts per million or molarity, and of course also include mole calculations if necessary. The first 5 questions are going to deal with Table G, and in Table G you're going to be looking either at temperature and figuring out the solubility, or you're going to be given solubility and you need to figure out the temperature. The first question is asking for the grams of KCl, so we're looking for the value on the y-axis that can be dissolved in 100 grams of water, which is what our graph is based on, at 30 degrees Celsius. So we're going to find 30 degrees Celsius and follow that up to the curve for KCl, which is this one, and then over to get a value. I would say that's probably around 35, 36. And don't forget to give it units. We don't like our numbers to be naked. All right, next question. At what temperature does 100 grams of sodium nitrate completely saturate 100 grams of water? So again, it is based on the 100 grams, so we're just going to be reading the graph, but this time we were given the amount of our solute, and we need to find the temperature at which that is saturated. So here's 100. Follow it over to the line for sodium nitrate and down, and I'd say that's at about 34. So that's 34 degrees Celsius. All right, the next question, they're asking what effect lowering the solution temperature would have on the solubility of O2. And what's really important here is that phase of matter. It's a gas. For lowering the temperature, it would increase the solubility. And the reason why is it's a gas. Don't forget to do that explain part, because I can't give you credit for the answer without the explanation. Next one, what effect will raising the pressure have on the solubility of Kf? And what's really important is the phase, which is a solid. Pressure only affects gases, so there will be no effect. And your reasoning could just be it's a solid. And recall that gases like high pressure. All right, next question. If 30 grams of NaCl are added to 310 grams of water at 50 degrees, is the resulting solution saturated or unsaturated? This is taking quite a leap from the other questions. The other ones are all pretty easy. Keep in mind that the fact that we're talking about a different amount of water doesn't matter right away. All that we need to do to start with is read our table. So we have 30 grams of NaCl at 50 degrees Celsius. For questions like this, my suggestion would be to find what saturated is for the substance, in this case NaCl, at the temperature given. So at 50 degrees, NaCl would show saturation at about 37, 38. So we'll say 38 is saturated in 100 grams of water. So we want to know what is saturated in 310 grams of water. And when we solve this proportion, I like to do it the super lazy way, and I'm going to do 38 times 310 and divide by 100 in order to get the answer. So the value that we get, 117.8 grams, is the amount of NaCl that would saturate 310 grams of water. They said that they have 30 grams, and they want to know if that's going to be saturated or unsaturated. Since that's less than the saturation point that we just calculated, it would be unsaturated. Oh, I gotta move this, or whoops. And as long as you show some work, like I did here, you'll be fine for your explaining using Table G. All right, the next few questions are going to be based on calculating concentrations. So we're going to be using the equations from the back of our reference tables. We may be using the mole calculation, but we'll definitely be using parts per million and molarity. All right, let's look at our first question in this section. What's the molarity of a 200 milliliter solution that contains 32 grams of NaCl? When we look at our molarity equation, the equation is molarity is equal to moles over liters. We don't have moles or liters given to us in this question. We were given milliliters and we were given grams. To convert to liters, all you're going to do is move it 3 places to the left, so it's 0.200 liters. It's not as easy to convert grams to moles, though. We're going to have to use our mole calculation, which is moles is equal to G over GFM. Our given mass is 32, and now we need to calculate the GFM of NaCl. All we're going to do is add the masses of the two atoms. The atomic mass of sodium is 22.99, and chlorine is 35.45, so we add those up, and we get 58.44. So that's the GFM that we're going to use here in order to calculate our moles. So we have 32 divided by 58.44, and we get 0.548 moles. Okay, now we're a little closer. We can now calculate molarity, which is big M, and the values we need are the moles divided by liters, and I just got that from this equation here in our reference tables. The moles we calculated is 0.548, and the liters we calculated were 0.200. So 0.548 divided by 0.2, and our molarity is 2.74. The units would be big M. You could also just give your units as moles per liter, but I like big M. It's a little less work. All right, next question. How many liters of a 1.2 molar solution of KCl can be made using 15.3 grams? So this time we were given the molarity, so we have this part of our equation already. We were given grams, which means we'll have to use that to calculate moles, and we're actually solving for liters for this question. So we're going to start first. We're going to calculate our moles. Moles is equal to G over GFM, where we have our given mass is 15.3, and we need to calculate the GFM of KCl. K is 39.10 and Cl is 35.45. So when we add those up, we get 74.55. So to get our moles, 15.3 divided by 74.55, we get 0.205 moles. So now, using our molarity equation, we have molarity as 1.2, so we're going to plug that in for molarity. We have our moles, we just calculated as 0.205, and we're solving for liters. A lot of times this is a difficult operation for students to solve for something in the denominator, and probably the easiest thing for you to do would be to cross multiply. So go ahead and put your molarity over 1 and cross multiply, and you'll get your 1.2 times the liters, and you're going to set that equal to the 0.205 moles. And then to get liters alone, you divide by 1.2. So we're going to have the 0.205 divided by 1.2, And we get our liters to be, I'm running out of room here, I write too big, 0.171 liters. All right, next question. We're calculating parts per million this time. They've given us our grams of solute, and they've given us our grams of water. The only tricky thing about parts per million is that if they don't give you the total mass of your solution, you have to add the solute mass and the solvent mass in order to get the mass of solution. Typically, it won't end up making any difference in your number because you use parts per million when you have a really, really small amount of solute. So to figure out parts per million, we're going to need our grams of solute divided by our grams of solution, all times 1 million. Our grams of solute were given as 0.00078. And we didn't get the grams of solution. We got our grams of water, but we really should be adding in the grams of solute. So we should have 450.00078. You're going to see that if you didn't do that, you're probably going to get the same answer that I do anyway because the values are so small. So now we're just plugging and chugging. We have 0.00078 divided by 450.00078, and you want to hit the equals times 1 million. And I get 1.73, and the units are ppm, or parts per million. Next question, and this one, they're looking for the amount of mercury present in a 500 gram solution, and they've given us our parts per million. This is probably the hardest solution for you to calculate with parts per million because you're going to be solving for this value here. And a lot of times students don't know what to do with this million. So pay attention as I solve this. For this one, we were given our parts per million is 10.0. We're looking for our grams of solute. If you want, you can go ahead and make that an X. Our grams of solution were 500, but don't forget about this 1 million. In fact, it might be easier if you think about this 1 million as being part of our numerator. And I think that'll make it easier for you to solve for X. We would normally, in order to get rid of something in the denominator, we would just multiply by it. That's the inverse operation. So we're going to multiply the 500 times the 10. And we'll still have the X times the 1 million. In order to get rid of the million now, we're going to divide by 1 million. And we need to do that to the other side as well. These cancel out, and now we just need to do the math. And it'll be 10 times 500. And then don't forget to divide by 1 million. And the answer you will get should be really small, 0.005. And that's grams. We were solving for the grams of solute. Last question in calculating concentration. They want to know how many grams of KClO3 would be needed to make a 0.3 liters of a 1.2 molar solution. This is very much the kind of thing that chemists have to do very regularly. Every lab, we have to figure this out. So this is actually a really real world question for a chemist or a first-year chemistry student in college. In this case, we were given the molarity and we were given our liters. So we have this value and we have this value. To start with, we're going to solve for moles, but what we're really looking for is grams. So once we've solved for our moles, we'll figure out our GFM and then solve for the given mass. So let's start first. We have molarity is equal to moles per liter. Our molarity is 1.2. We're solving for moles, and our volume was 0.3 liters. So to solve, to get moles alone, in order to get this alone, we would multiply by 0.3. And when we do that, we'll get 0.3 times 1.2. And the number we get is 0.36, and that's moles. That's not what we're looking for, though. We're looking for grams. So using our moles calculation here to solve for the grams, we have 0.36 moles is equal to, we're solving for grams. Now we need to figure out the GFM of KClO3. Potassium's mass, we said before, was 39.1. And then chlorine's is 35.45. And then we have 3 oxygens at 16. So doing the math, it's always a good idea to try it twice before you're sure, and I did try it twice. It appears correct. So to solve for grams, we're going to get grams alone here, I would multiply by this, and when I do that to the other side, I'd have 0.36 times 122.55. So my answer, if I wanted to make a solution, that I ended up with 0.3 liters, and its concentration was 1.2 molar, we'd end up with needing to add 44.12 grams of the KClO3. So once I've figured that out, I can go over, mass that out, add it to my volume of water, and I've made my solution. The next few questions are going to be based on vapor pressure and table H. So we're going to use table H. At what temperature would ethanoic acid boil if the atmospheric pressure was 70 kilopascals? Recall that the y-axis is by intervals of 10 and the x is by 5s. So we've been given the pressure and we just need to find the temperature at which it would boil. So 50, 60, 70, follow that over to ethanoic acid and down, and you're going to get about 107, and that is degrees Celsius. Next question, the normal boiling point of ethanol. Normal boiling point is the boiling point at 101.3 kilopascals, or standard pressure. So we're going to follow that over to ethanol and down, and it's just shy of the 80 line, so we would say 79. And again, that was degrees Celsius. If propanone boils at 45 degrees Celsius, what's the atmospheric pressure? Remember that boiling is when vapor pressure equals atmospheric pressure. So when we look at 45 degrees, which would be right here, and follow that up to propanone and over, that would be 70 kilopascals. Number 14, what phase of matter would water be at 75 degrees Celsius if the atmospheric pressure is 10 kilopascals? Recall that when the point is to the left of the boiling line, it's a liquid, and when it's to the right, it's a gas. So we're doing 75 degrees and 10 kilopascals. So here's 75 degrees. This is 10 kilopascals. That would be to the right of the boiling line for water, so that makes it a gas. And to justify your answer, you can say it's to the right of the curve. Next question, at what temperature would ethanol boil if the pressure is 150 kilopascals? So 150, oh, I need to make that a little, 150 kilopascals, follow that over to ethanol and down. Keep in mind that the interval down here is by fives, so that would be 90. And don't forget your units, we're talking about degrees Celsius. Now we're done with vapor pressure. These last questions are going to be about colligative properties, or the fact that when you dissolve solutes in water, it'll increase the boiling point and decrease the freezing point. First question, if there were 2 moles of calcium chloride dissolved in water, how many moles of dissolved solutes would there be? When they say dissolved solutes, really what they're looking for is that working molarity that we discussed in class. So when it dissolves, if it breaks into more particles, you're going to multiply those number of particles by the concentration, or in this case, the number of moles. So CaCl2 is ionic, which means it will break up as long as it dissolves, and calcium chloride does. In this case, we're going to have 1 Ca and 2 Cls for a total of 3 particles. So if we have 2 moles of CaCl2, when we dissolve that, we can multiply it by the 3 particles, and you'll essentially get 6 moles of particles. This is our answer, and this is our work. You're not going to get any points without any work. Number 17, which solution would have a lower freezing point, 1 molar sodium hydroxide or 1 molar glucose? And justify your answer. Sodium hydroxide is ionic, and glucose is covalent. So the ionic one is going to break up, in this case, into 2 particles, Na plus and OH minus, where the glucose isn't going to break up at all. It's covalent. The one that will lower the freezing point more is the one that has more particles. In this case, that would be NaOH. And if you wanted to use your math like we did above, you're going to actually multiply it by the 2 particles, and you have a working molarity of 2 molar. The last few questions are multiple choice. Compared to the freezing point and boiling point of water at 1 atmosphere, a solution of salt and water, so dissolving something in it, when we dissolve something in water, it increases the boiling point and it decreases the freezing point. And the one that says that is choice 2. Number 19, which solution has the highest boiling point at standard pressure? We're going to look for the one with the most dissolved solutes. All of these have the same initial molarity, so we're just going to be comparing the working molarities. So what you're really doing is counting the number of particles. All 4 of these are ionic. All 4 of them are. These ones have polyatomic ions, NO3, PO4, and SO4. So we're going to count those as one thing. So we have K and Cl in the first one, so there's 2 particles there. We have K2 and SO4, so there's 3 particles there. Here we have 3 Ks and 1 PO4 for 4 particles. And the last one we have K and we have NO3 for 2 particles. So the one that's going to make the most is choice 3. Last question, how do the boiling point and freezing point of a solution of water and calcium chloride at standard pressure compare to the boiling point and freezing point of water at standard pressure? Again, we're looking at how when we dissolve something in water, it increases the boiling point and decreases the freezing point. So that one is choice 4.